All right, we are working in section 7.8. We're going to be working with what are called improper integrals. And the definition of an improper integral is simply an integral in which one of the limits of integration is infinite. Our basic definition for our definite integral requires that we have a finite interval from a to b, but in an improper integral, the limits of integration may have an infinity or a negative infinity involved. Right? We're going to take a look at how to handle these, and unsurprisingly, it is going to involve limits. If I have infinity for my upper limit of integration, then notice that what we're going to do is just replace infinity with some random constant. We typically call it b, and then we take the limit of this integral as b goes to infinity. That's going to allow us to find the integral or area under this curve from a on forever as b moves out towards infinity. Now that area may be infinite, but it's possible if this squeezes down small enough, it may actually have a finite limit. Opposite over here, if my interval is negative infinity to b, then I'm going to have to replace the negative infinity with a constant we'll call a and take the limit as a goes to negative infinity. Here we're looking at the area under the curve, all the way from negative infinity coming up to b. It's also possible to have an integral from negative infinity to positive infinity, so literally the area under the entire curve forever, in which case we have two limits that we have to replace, both the top and the bottom. So what we do is we pick a random value c. C is truly anything you want it to be. In our picture, it's right here. C is just any real number. And we first integrate from a to c, with a going to negative infinity. And then we integrate from c to b, with b going to positive infinity. So we're essentially finding this area in two pieces, the piece to the left of c and the piece to the right of c. One quick note, it's often convenient to pick c equals 0. In many cases. And so that's typically what I'll try first unless there's some strong reason not to. All right. If the results that we get when we do these limits of these integrals turn out to be finite, then we say the limits converge. If they're infinite, they diverge. So I'm going to clarify this just a little bit. It says if the limits in these cases exist and are finite. Then the improper integral converges. If they're infinite, they diverge. So in summary, if the limit is finite, the integral converges. And if the limit is infinite, positive or negative, then we say the integral diverges. All right, let's try a few examples. In our first example, it's our upper limit of integration that's infinity. And just to kind of get a picture of what's happening, let's do a quick graph of the integrand. I know it's an exponential decay function, but I'm just going to quickly put it on a calculator graph. Y equals e to the negative 3x. And unsurprisingly, we get this exponential decay picture, like so. We're integrating from 0 to infinity, so we're really just looking for the part over here. And we know that that function doesn't ever actually hit the x-axis, but it comes really, really close. It gets very tiny. And so it's certainly possible that that area has a limit, since it's squeezing down to not quite 0, but very close to 0 as the x values go to infinity. Let's find out. So the first thing I'm going to do is say I can't have infinity as a limit of integration. So I'm going to replace it, and I'm going to say let's take the limit as b goes to infinity, and then I'll change this to the integral from 0 to b. All right, so I've got the limit as b goes to infinity, and my antiderivative for e to the negative 3x is itself. Think through that mental U substitution. The derivative would be negative 3. You'd have to divide by the negative 3 to move it to the other side. So you'll end up with a negative 1/3 when you made your du. And that gets evaluated from 0 to b. So I've got the limit as b goes to infinity of, plugging in the b, so, and then subtract a negative would be plus 1/3 e to the 0. So I have negative 1/3 e to the negative infinity, that would be 0, plus 1/3 times 1, which just gives me 1/3. So even though that area goes on forever, it had a finite limit. That is the area under that graph, from 0 on forever. All right, let's try another one. This time my integrand is 1 over 1 plus x squared. And let me change my window just a little bit. I don't need it quite so big. There we go. And we can see what this looks like. Like that. And this time we want to go from negative infinity to infinity. So we want the entire area from the left side to the right. Okay, on forever. Again, the ends get squeezed down very small, so it's possible that I've got a finite limit, although not guaranteed, as we'll see a little bit later. So, because both limits have infinities in them, I technically need to replace them both with a variable. But I'm going to use a little trick here. Instead of doing two separate integrals, one from negative infinity to 0, say, and the other from 0 to infinity, would you agree with me that because of the symmetry, the area on this side, on the left, has to be equal to the area on this side? They're identical, right? Due to symmetry. Therefore, what I could do, instead of setting this up as two separate integrals, is maybe I'll just do the part over here on the right-hand side, from 0 to positive infinity, and then I'll double it, knowing that the left side's the same. So I'm going to say let's do 2 times the integral, and we'll only go from 0 to infinity. And that'll save me some repetitive work. All right, I still can't have infinity in my limit, so I'm going to have 2 times the limit as b goes to infinity, and then integral from 0 to b of 1 over 1 plus x squared dx. That's one we've seen a few times, right? That's the arctangent. You can always look it up, but that's the arctangent integral. So using my FTC, I'd have arctan B minus arctan 0. I need the limit then of the arctangent function as b goes to infinity. And as we often do, I'm just going to use a graph to analyze that. Let's go ahead and graph the arctangent function. Let's see. Now let's start like that. It does seem to be leveling out as b goes to infinity, but I don't know for sure. Does that increase without bound, or does that actually kind of level off at a particular value? I'm going to go ahead and change my window and go out a bit further on the x-axis, maybe out to 20. And it certainly appears to be leveling off. If I were to trace this, it might help a little. But I may need to use a little bit of my mathematical knowledge to figure out where it's leveling off. It almost looks like 1.5, but I actually don't think that's right. In fact, if you remember the arctangent function, it's just the inverse of the tangent function, right? The tangent function has vertical asymptotes at pi halves and negative pi halves. And so remembering that the inverse just flip-flops the x's and the y's, when I'm seeing this picture that I'm seeing here, the vertical asymptotes would become horizontal asymptotes. But they're still going to be at negative pi halves and pi halves. And now my picture looks like that. So based on that analysis, I think rather than 1.5, notice it went past 1.5 here, it's already at 1.51, I think that's actually going to be pi over 2, where that levels off. So this first limit, we're going to go with pi over 2. And the arctangent of 0, either you know or you can use your calculator, is 0. If you look at the graph here, my orange graph, the arctangent is 0. The orange one is y equals arctangent x. So the 2's cancel out, and I'm just going to get pi. The area under that whole graph, both sides, because I've doubled, is pi. All right. On the next page, I'm actually going to do this just slightly differently than what the instructions say. It says experiment. We're actually going to do it a little bit more formally. But we'd like to determine when this integral converges and when it will diverge then. Notice that both of the integrals that we just finished converged, right? This had a finite answer, so it converged. This one also had a finite answer, so it also converges. We're going to now look at a specific type of integral, 1 over x to the p. And I want to know, when does this converge? And then by contrast, when does it diverge? So first of all, I know that this integral is going to have to be, oops, you know what? There's a typo. That should be an infinity up there. Otherwise, it's not a very interesting question. I wanted the improper integral from 1 to infinity. So I'm going to start by rewriting this as the limit as b goes to infinity of the integral from 1 to b. And let's write that as x to the minus p dx. As long as p is not 1, I can use a power rule on this, right? If p is 1, that's the natural log integral, so we probably have to check out that later. So as long as p is not equal to 1, I can do this just using the power rule for integration. I would add 1 to the power and divide by the new exponent. And my limits of integration go from 1 to b. All right, so I'd have the limit as b goes to infinity. Plugging in the b, I'm actually going to write this in a very specific way. This denominator is just some constant. So I'm going to write this as 1 over 1 minus p times b to the negative p plus 1. Subtract, same thing here, 1 over 1 minus p times 1 to the minus p plus 1. This is just going to be 1. 1 to any power is 1, except for infinity, and p is not infinity. P was whatever power was on that x. So let's do this. Let's factor out the 1 over 1 minus p. Since it's a constant, p is just some number, I can actually factor it all the way out of the limit. And then I'd have b to the minus p plus 1. Subtract, that's factored out, so I just have 1. All right, this is where we're going to have a couple of different cases. What happens to this as b goes to infinity? Well, if that exponent is positive, the infinity is in the numerator, and it will stay infinity. But if that exponent is negative, it's really in the denominator, and infinity in the denominator goes to 0. So, first of all, let's say if the exponent, minus p plus 1, is greater than 0, or in other words, if 1 is greater than p, then I would have a positive exponent and infinity with a positive power is still infinity, and this diverges. However, if the exponent is negative, less than 0, in other words, 1 is less than p, then we end up with infinity to a negative power, which is 1 over infinity to some power, which goes to 0, and this converges. So that's almost everything. We know if p is bigger than 1, it converges. If p is smaller than 1, it diverges. The only thing we don't know is what if p equals 1. So let's do that, and then we'll summarize our results. If p equals 1, then the original integral from 1 to infinity would just be 1 over x to the first power. And if I do my usual thing here and replace the infinity with a limit as b goes to infinity, I know that integral now doesn't follow the power rule, that's just the natural log. So this time, I would get the limit as b goes to infinity of ln b minus ln 1. Now as b goes to infinity, the natural log function slowly increases as well. That's infinity. Natural log of 1 is 0. So this goes to infinity and therefore diverges. So in summary, the integral that we're interested in only converges if p is strictly bigger than 1. If p is equal to 1, or if p is less than 1, it diverges. So let's write that up as a summary. The integral from 1 to infinity of 1 over x to the p dx converges for p is greater than 1 diverges for p is less than or equal to 1. So a nice little mathematical thing that we can discover just by, it's not quite trial and error, it's a little bit stronger than that, but a little bit of mathematical manipulation. We're going to keep this one in mind because this is also going to kind of come back and be useful to us in the next chapter, this result. All right, example 6 is going to bring us back a little bit. We're going to go back to our days of surfaces of revolution. Back to the beginning of the course, right? And I would like to find a couple of things based on R being the region bounded by the graph of y equals x to the minus 1, or y equals 1 over x, and the x-axis, specifically for x greater than or equal to 1. I would like to find the volume of the solid generated when that region R is revolved around the x-axis, and then also the surface area of the solid that's generated when R is revolved around the x-axis. Just so you know, that part B is going to take us a bit, so I'm going to eliminate part C. You can cross out part C on this page. You'll be able to use the whole space for part B. All right, let's get a visual on this. Y equals 1 over x. Just looks like this. And I only want to find the, I only want R to be the region for x greater than or equal to 1. 1 over 1 is still 1. So I'm looking at my region looking like this, and then going on forever. Okay. When I rotate that region around the x-axis, I'm going to end up with something that kind of looks like that, right? Kind of a horn-shaped thing or a trumpet-shaped thing. In fact, there's a name given to this. This is a very famous mathematical problem. We call this Gabriel's horn. All right, so my goal right now is to find the volume of Gabriel's horn. I'm going to do this using a disk method. So let's see. If I were to draw my little representative rectangle here perpendicular to the axis of rotation, then the volume of the disk, pi r squared h, would be pi times the radius of my disk is actually the height of that rectangle, the y value, 1 over x, squared, and the height or thickness of the disk is just the little delta x. Okay. So the overall volume for the whole thing, I would want to integrate from 1 to infinity. The volume of my disk, I'm going to pull the pi out in front, and then that would become 1 over x squared, and my delta x becomes a dx, infinitesimally small. All right, based on the last problem we just did, we already know this converges, right? This is like a p-value of 2, and since that's bigger than 1, we're in the convergent case. Let's actually do the integral to find out what it converges to. I would have pi times, I'll make this the limit, as b goes to infinity, integral from 1 to b. Let me rewrite that as x to the negative 2 dx. Integrating that would give me minus x to the minus 1, evaluated from 1 to b. So I'd have negative b to the minus 1, or 1 over b, minus a negative is plus 1 to the negative 1, or 1 over 1. As b goes to infinity, 1 over infinity becomes 0, plus 1, and pi times 1 is pi. So the volume of that solid, that Gabriel's horn, is pi cubic units, whatever they happen to be. So even though this is an infinite object, right, the kind of thin part here of Gabriel's horn goes on forever, it's actually got a finite volume. You could fill it up with something. The volume is finite. All right, let's take a look at the surface area of the same solid. First of all, just a quick reminder, the volume of a disk is something that we probably use often enough, so we don't really need to look it up. Probably at pi r squared h was pretty familiar, but we haven't talked about surface area for a little while. So I just want to remind you, our surface area formula for a rotational solid around the x-axis looks like this. Let me just go ahead and put that down real quick so we have it to work with. It was 2 pi, integral from a to b, of f of x, square root of 1 plus f prime of x squared dx. All right, in this case, just a reminder, our function f of x was 1 over x, or x to the negative first. And so plugging in everything that I need here, I would have 2 pi, and I know that that's going to be the integral from 1 to infinity again. So why don't I just go ahead right away and make this the limit as b goes to infinity. And then I can go from 1 to b. Save me one rewrite. F of x, that's my x to the negative first. And then the square root of 1 plus f prime. F prime would be minus x to the minus 2, and that gets squared dx. All right, so I've got my 2 pi times my limit, and let's see here. Think a little bit about what I want to do with this. I think what I'll do is I think I'm going to put this x to the negative first. I'm going to move that into the denominator and just leave the radical on top. 1 plus, squaring that would make that positive x to the negative 4th power. And then x to the negative first, I'll just make that x to the first on the bottom. Now, I need to integrate this. And right now, I'm not seeing anything that looks great. You can look through your table of integrals if you want to, but I'm going to tell you, you're probably not going to find anything that looks just like that. So I'm going to use a little trick. I'm going to say, let's multiply by a form of 1. If I do that, I'm going to choose the form of 1 that's going to get rid of that negative exponent. So under the radical, it would be x to the positive 4th power. The denominator doesn't have a radical, so that's the same as x squared, right? Those are really the same things, so it's a form of 1. Under my radical now, I have x to the 4th plus that becomes x to the 0, which is just 1. And in the denominator, I have x cubed. All right, a little bit better, but not quite what I want yet. In actuality, I think I'm very close to one of the integrals in the table, but I'm not quite there. The one I think I'm pretty close to is this number 81. Right here. Okay. I've got the a squared plus x squared. That would be a squared would be 1, and I could think of this as x squared squared. But I would need that same x squared in the denominator, so I need an x to the 4th down here to pull that off. I'm going to go ahead and say, let's go for that. Let's try and make that an x to the 4th. And in order to do that, I would actually have to multiply top and bottom by x. Just because this is a long problem, knowing where I'm headed, I'm going to cheat just a little here. And I'm going to squeeze in that times x on the previous line as well. So let's also multiply by x over x. That's going to put an x out here on top, and it's going to make this an x to the 4th power. All right, I'm now ready for a u substitution. Again, my goal is this number 81, and so I really need a u squared under here, and instead I've got x to the 4th. So I'm going to let u be x squared, and that way this will become a u squared. That way du is 2x dx, and 1/2 du is x dx. I've got that x dx right there, so that'll become my 1/2 du, so that's a good thing. And let's see if this all worked out. All right, under my radical, I would have u squared plus 1. In the denominator, I've got u squared. And then the x dx becomes 1/2 du. Put the du here, and the 1/2, I'm just going to put a divided by 2 way out in front. So it's all there. All right, I think that worked really, really well, because if I now compare to this number 81, I think I've got exactly what I need. Right here. A squared plus x squared, that's just fine. My x is actually u and my a is 1. And in the denominator, I have u squared instead of x squared, so other than the different variable, I have u instead of x. Everything else looks great. So we should be able to use this number 81 now to write down our antiderivative. I can let those 2's cancel, so I've got pi. Limit as b goes to infinity. And then my antiderivative is the natural log of the absolute value of, and I'll have u plus the square root of 1 plus u squared minus the square root of 1 plus u squared over u, and instead of plus c, I've got my limits of integration from 1 to b. All right, whew. We finally got the antiderivative. That was a challenging one. Let's see what we can do with this limit. All right, plugging in the b, I'd have the natural log of b plus the square root of 1 plus b squared minus the square root of 1 plus b squared over b. Subtract what I get when I plug in the 1, which would be the natural log of 1 plus, the square root of 1 plus 1 would be 2, minus square root of 2 over 1. Actually, you know what? We're going to go ahead and do the limit, so I'm not going to write the limit here. As b goes to infinity, this all just becomes the natural log of infinity. So that's all going to go to infinity. Okay. Now, as long as I don't have infinity minus infinity, this will be an infinite limit. But we got to make sure it's not infinity minus infinity. So let's check this out. This part right now is infinity over infinity. That's an indeterminate form. I could use L'Hopital's rule, but remember what happened last time? Last time I tried to use L'Hopital's rule, I had a problem with the radicals. So I think instead of that, I'm just going to use our old method. I'm going to say if I were to divide the top and the bottom by the highest power of b, let's just go ahead and do this. I would have, let's see, we divide by square root of b squared on top and just plain b on the bottom. That would become the square root of 1 over b squared plus 1 over 1 minus all of this like so. All right, this is what? Square root of 0 plus 1? So I just have 1. So I end up with pi times infinity minus 1 minus the natural log of 1 plus the square root of 2 minus the square root of 2. Looks like a mess, but the good news is infinity minus anything is still infinity. So this limit is infinite, and this diverges. All right, that was a lot of work for that problem, but good for us to tackle this every once in a while. And here's the interesting thing about this shape, this solid of revolution, Gabriel's horn. Remember that we got a finite volume. The volume was pi. But I just got an infinite surface area. So if you imagine the shape, what we've just done is created an infinite shape. Again, this really goes on forever, right? Keeps on going out here. It's got a finite volume, so I could fill it up with paint, but it's got an infinite surface area, so I could never paint it. It's kind of an interesting paradox. All right, I'm going to leave you with that paradox for this video, and we'll come back and finish the section in the next one.